I'm starting the class today. As I was discussing on steam turbines in the last class I started, and in that class I tried to make it out what is the meaning of impulse and what is the meaning of reaction. Okay, now we will show uh, the simple impulse turbine and how the impulse turbine are modified for specific purposes to minimize loss, etc. We will show. So in the last class, I discussed on this, that is impulse turbine. Here I'm just recapitulating. Impulse turbine, here you have a nozzle through which the fluid is coming out and it is impinging on the blade, and therefore the momentum of the fluid is transferred to the blade. So here what we have to understand the corresponding diagram in the PV, that is pressure and velocity. We will try to understand that. It is very important to understand how the pressure and velocity is varying. Okay, I think it is uh, completely visible. Now, impulse turbine, try to see what is happening. So in the impulse turbine, there are two things in a particular stage. This is called a stage. So where you have a water uh, ejecting mechanism, that is a nozzle, and there is a moving component, that is the blade. So taking these two together is called a stage. Okay. Taking these two together is called a stage. So here in this diagram, one stage is shown. Okay. Now, what is happening to the velocity and pressure? Let us see. Now, as we know that for a nozzle, what happens? In the nozzle, the pressure is reduced and the at the exit of the nozzle, the velocity is increased. So that is happening. See it. Try to follow one by one. So this is the nozzle part. This green part is the nozzle part, and this is the blade part or the moving. This is called the stator, and this is called the rotor. So they are basically placed like two discs in the on the same shaft. It is not like in the same plane. They are at different planes. Okay. So let me show. They are actually having different planes, parallel planes. So in one plane, is like this. It is one plane. It is another plane. So the nozzle is with one plane. Let me show it more clearly. Say, for example, this is the disc which is accommodating the nozzle. and this is the one. Along the same axis but at different planes. Here you have the blades. So blades are on this plane. So they are separated in the axial direction, and the axial direction is like this. Axial direction is like this. They are separated in the axial direction and parallel to each other. Therefore, a fluid will come out from the nozzle and will strike on the blade. So you can see that the fluid will come out from the nozzle and it will strike on the blade. Therefore, it will exchange or impart its momentum to the blade, and therefore the blade initially, which was not rotating, it will start rotating and continue to rotate for the time of operation. So that is the function. Okay, the first thing must be clear. So these two are basically, this diagram, try to understand, this diagram is drawn on the meridional plane. What is that meridional plane? In the last class I discussed. This is parallel to the other, tangential to the curved surface of the cylinder. So this is the meridional plane on which it is shown. So everything we are basically drawing on the plane tangential to the curved surface, and we are drawing it. Okay, so it is basically seeing from the top, and we are basically sh- showing it after cutting it and stretching along the tangential direction. We are seeing or viewing the stator, that is the nozzle set and the blade set. So that must be understood properly. Okay. Now, first of all, is it clear how the blades and the nozzles are mounted and how they are basically placed? So nozzle is here and exit of the nozzle will strike the blade and the blade will rotate. So that is the mechanism. So it is in this way. Now, what is the function of a nozzle? For the nozzle, there will be, say this is coming from the steam chest, that is called steam chest, or from the steam generator is coming and collected it at the steam chest. So steam chest. Here in this part, the pressure is constant. In this part, the pressure is constant. Now, when it is passing through the nozzle, there is a pressure drop, and that pressure drop will result in a increase in velocity. So pressure will reduce and velocity will increase. That means it is called expansion process. The pressure will reduce, and in turn, or in effect of that, or due to the pressure reduction, there will be increase in the velocity. That means kinetic energy of the fluid will increase due to the pressure fall. So that is the work of basically the nozzle. Now, after that, what will happen basically? The So pressure is reduced. As you see, pressure, this color, this uh, purple color line, pressure is reduced here and velocity is increased. So opposite things are happening because it is conserved, energy is conserved. So one energy is converted to other. Okay. Next, basically, what is happening? This is happening within that means this change is happening within the nozzle only. We have not yet touched the blade. So this part is up to the nozzle. You can verify from a particular straight line. So you can see it. This is the nozzle. So whatever happening is within the nozzle. This change is happening within the nozzle. Before nozzle, there is no change and the pressure and velocity were constant. Pressure and velocity were constant. Then within this nozzle, there is a change. That means it is said that the steam suffers a pressure drop and the kinetic energy of the steam is increased. That means its velocity is increased due to the reduction in pressure. Now, after that, what happens? As the steam strikes the uh, blade, now the blade will get some of its kinetic energy and therefore the kinetic energy of the blade will increase and the momentum of the fluid or the momentum or the kinetic energy of the fluid will drop. That means velocity of the fluid will drop. That means what is happening? The kinetic energy now is transferred to the blade. Therefore, in the blade passage, the fluid will suffer a reduction in velocity, but during this time, the pressure will remain constant. That is the most characteristic feature of a impulse turbine, that you have to clearly understand that during the blade, during the movement of steam in the blade passage, there will be only velocity change, but there will not be any pressure change. Pressure remains constant. Okay. Because there is no expansion of steam. If the pressure, if there is no expansion, then the pressure will remain same. So this purple color line you can see is clearly pressure remains constant. Only velocity is decreased. Okay, is it visible properly? Is it visible properly?
Yes, sir.
I think you have understood it.
এতে প্রেসারটা কনস্ট্যান্ট থাকে বলছেন তো?
ব্লেডের মধ্যে প্রেসার কনস্ট্যান্ট থাকবে। For a impulse turbine, this is the characteristic feature that within the blade there will not be any pressure drop. If, remember, if there is a pressure drop in the blade, that makes it a reaction turbine. Within the blade, if there is a pressure drop, then it will make it a reaction turbine. Basically, that is the principle of reaction. That means within the blade passage, there will be a pressure drop and there will be a corresponding reaction on the blade. That means due to the pressure drop, there will be a reaction on the blade, and that is the characteristic of reaction turbine. So the characteristic feature of an impulse turbine is that the pressure drop will be within the, now let me enlarge it more and you will get the clear figure. Okay. During this movement, only there is pressure drop. So pressure is this purple color line that is changing only during the passing through the nozzle. In the blade, there is no pressure drop. This is to be remembered, understood. This pressure change occurs due to the expansion. So during the movement of steam through the blade passage, there is no expansion. Only it is diverted by the blade. So kinetic energy is reduced because part of the kinetic energy is transferred, or part of the momentum is transferred to the blade. So the velocity is reduced. So what is happening, you have to follow carefully. This is the basic of this impulse turbine. So in the nozzle passage, the the pressure drops and velocity increase. That is why it quite clear, because we have studied in the compressible flow, that is the function of a nozzle. But what is the use of blade? Now, the kinetic energy that we have obtained at the end of the nozzle, now we want to use it for rotating the blades. So, part of the kinetic energy, part of the momentum of the fluid now will be transferred to the blade, and therefore the blade will rotate, and therefore the velocity of the steam will drop. Now remember that the diagram here that we are showing is the velocity and pressure of the steam only. Whatever is happening with steam, that we are showing. This velocity is not corresponding to the blade. Okay, so during the movement of the fluid in the blade passage, there is velocity decrease because the momentum partially has been transferred to rotate the blade, and therefore the fluid or the steam will suffer a drop in kinetic energy or reduction in kinetic energy and momentum. Okay, so that is the function of impulse turbine. Okay, next. In the reaction turbine, actually what happens, this is the nozzle. This green part is the nozzle. And in the nozzle, as usual, the nozzle part is same for the impulse and the reaction turbine. Nozzle part is same. Okay, let me show it. Nozzle part is same. So here, let me draw. This is the nozzle part. Now follow what is happening in for pressure and velocity. Now what is happening in case of pressure and velocity? Let us try to see. So okay. Now you see that I have differentiated, I have demarcated three different zones. One is before the nozzle, another is within the nozzle, and the third one is in the blade passage. Okay. So within the steam chest, that is in this zone, there will not be any change in pressure and velocity. So as if there is no flow, and even if there is a flow, the flow is very small. That is, the flow is very weak. So flow is very slow. Therefore, there will not be any substantial pressure change or noticeable pressure change and velocity change as compared to the changes within the nozzle and the blade. So first look at in the nozzle stage. In the nozzle stage, as usual, there will be a pressure reduction, and due to the pressure reduction, there will be a kinetic energy gain. So it will be the energy due to the pressure reduction will be converted to the kinetic energy, and the at the exit of the nozzle, the fluid will have higher kinetic energy as usual. Now, there is a difference in the blade passage. In case of impulse turbine, there was no change in pressure during the movement in the blade passage. But in the reaction turbine, again a there will be an expansion. That is, again there will be a fall of pressure, as if you have another balloon here. Okay, as if you will have another balloon kind of thing here. Consider that as if there is a balloon here, and the mouth of the balloon is like it is on this side, and let me draw it. So as if it is a balloon, it's like this. The balloon is like this. Consider the balloon is like this. It is situated here in between the blade passage. Here, there is the balloon. So the balloon is here basically in the passage. Now the mouth of the balloon is opened here, and therefore the gas is ejected in this direction. The gas is ejected in this direction, and therefore as a result of an opposite reaction, the balloon will have a force. It will face a force in the opposite direction, and the component in the tangential direction will make the blade to rotate in the tangential direction. So this will be the direction of movement of the blade due to the reaction. So the blade passage will act as an expander, and it will cause a pressure drop in the fluid, further pressure drop. So the pressure drop took place in the nozzle also, as well as in the blade passage. So there will be reduction in pressure, but you see the difference in velocity. What is happening in the velocity? The velocity of the fluid is not increasing due to that pressure change. Why? You see, here in the nozzle passage, the due to the movement, due to the pressure reduction in the nozzle, there is a velocity increase. But here also, due to the pressure reduction, I think you can see. Let me, yes. So I think you can see, right. Now see that within the nozzle, the pressure reduction causes a velocity increase. But within the blade passage, although there is a pressure reduction, but the velocity is also reduced. Why it is so? Now try to understand that. In the nozzle passage, what is the difference between a nozzle and a blade? The nozzle is static. So that means what? The nozzle is static. So even if there is a pressure drop, the nozzle will not move. What will happen? All the movement will be all the movement will be of the fluid itself. That means due to the pressure drop, the fluid velocity will increase. Okay. So velocity of the fluid will increase, but consider the moving blade. In the moving blade, if there is a pressure drop, what happens? That pressure drop causes the blade to move in the opposite direction, as if the balloon is moving in the opposite direction. Now, if the balloon itself moves, so what will be the absolute velocity of the fluid of the balloon that is coming out? That will not be that much. If you hold the balloon, if you say allow, if you hold the balloon and allow the fluid to be ejected from the mouth, then the velocity will be more. In comparison to the case when you allow the balloon to react, to react means to react against the velocity of the fluid that is coming out from the nozzle. So means coming out of the mouth. So if the balloon is allowed to move, then what will happen? The velocity is in this direction and the balloon is moving in this direction. And in that case, the absolute velocity of the fluid will be less compared to the case when you hold the balloon and allow the fluid to be ejected, because you are stopping the movement of the balloon, and therefore whole velocity or whole kinetic energy will now be of that of the fluid. Here, in case of nozzle, the fluid is getting the velocity and nozzle cannot move. So all the expansion is now causing the movement of the fluid itself. But in case of the blade can move. Therefore, the total kinetic energy gain due to the expansion is now shared by the movement of the fluid as well as that of the blade. Therefore, the kinetic energy of the blade, kinetic energy of the fluid falls, and that is now converted to the kinetic energy of the blade, means that is transferred. So here actually what is happening, try to understand that from this nozzle it is striking the blade. Striking the blade, that principle is known as impulse principle. That means when the fluid strikes the blade, that is called the impulse principle. And when the fluid moves and it expands in the passage and in reaction the blade moves, that principle is called the reaction principle. Therefore, don't you think that this is a combination of impulse and reaction? That means both the principles are present. That means the blade movement is due to both the impinging of this jet on the blade. Due to that, there is an increase in the velocity of the blade, as well as due to the expansion of the fluid from the moving blade also causes a increase in kinetic energy of the blade, or motion or setting motion of the blade. Therefore, this is not a pure reaction turbine. This is rather বলছি, this is okay, let me repeat. What is the function of impulse, or what is the principle of impulse? Impulse means, basically I told you in the last class that, say for example, you are beating or hitting a cricket ball with a bat, right? So that means what you are doing, you are basically striking the ball, and therefore the momentum of your bat is transferred to that of the ball, and the ball gets kinetic energy, and the bat kinetic energy or the bat momentum will be reduced a little. So that means as the momentum will be transferred, the ball will get the kinetic energy, and bat will have, after hitting, the bat velocity will reduce a little. So that is impulse. So according to the impulse momentum principle, you know that if I write mathematically, it will be clear to you. You see that basically from the Newton's second law, it is another version of Newton's second law. So is like this. We know it. ddt of mv, that is rate of change of momentum. What is that? Rate of change of momentum is force. We know from the Newton's second law, we know that rate of change of momentum is force. Okay. Now, if I write like this, ddt of d of mv is equal to f dt. And if I integrate this over some time, so it will give us on the left hand side the change in momentum. So that will be, say, mv2 minus mv1. What is the meaning of mv2 and mv1? I'm sorry. mv2 means basically momentum at time 2, at time instant 2, and mv1 means momentum at time instant 1. So during some say impact, there is a change in momentum. So before impact and after impact, if we integrate, then we will get the change in momentum. So mv2 means the momentum after impact minus say mv1, it is momentum before impact, and this is therefore equal to integral of f dt from t1 to t2. So this quantity is called the impulse. Okay, so this is the impulse. This is the impulse. This quantity. And this quantity is the change in momentum. This is one way of solving kinetic or dynamic problems. This is called impulse momentum principle. Here, basically, on the left hand side, it is the change of momentum, and this is the cause. So it is like on the right hand side, that is red shaded, that is the cause, and this is the effect. So due to the impulse, there is a change in momentum. Okay, that means what is happening, that F force over a time of dt, if it is striked, then there will be a change in momentum. So this will cause a change in momentum. Now you can consider that is happening. Okay, so here say when the jet is striking, so it is giving a force on this over some time, and therefore there is a change in momentum. So that is the impulse. So due to that, if the blade moves means what, mv1 mv2 minus mv1, so there will be a change in momentum, so its velocity will change. So that is causing the change in velocity of the blade, or that is setting the velocity in the blade. That is called impulse principle. Okay, is it clear? That means when you are striking that that means this is the blade, you want it to be moved. Therefore, what you are doing, you are as if aligning one nozzle over this, and it will rotate. Okay, so that is the impulse principle. It is there in hydraulic turbine also. Say Pelton turbine, there is that is impulse turbine. So it is striking on the basically blade. This is impulse. Okay, there is no, you see that due to this change there is no pressure drop. When this is striking the blade and the blade is moved, there is no pressure drop. Pressure remains constant. Okay. Now what is reaction? Reaction means on the nozzle there is a change in velocity, and that is striking the blade. So due to that striking, the blade moves. Along with that, in the blade passage also, in the blade passage, you see, in the blade passage also, in this zone, there is further pressure drop. That means when the fluid moves through this, it suffers a pressure drop, and therefore, as if like a balloon, you can consider as if there is a balloon, and due to the movement of the gas, the pressure reduces, and therefore there will be a reaction. So due to that reaction, the balloon will try to move in the opposite direction, but it can move only in the tangential direction. Therefore, its component in the tangential direction, the component of the reaction force in the tangential direction will make the blade move in the tangential direction, and therefore it will rotate. So this rotation of the blade is happening due to both the impulse effect as well as the reaction effect. That is why these are called impulse reaction turbine, but loosely they are called reaction turbines. But remember that there is this diagram is showing a reaction impulse reaction turbine, but here this one, it is a pure reaction turbine. Like this can be made, but in case of a effective uh, turbine, it is not possible. But this in this way you can understand the pure reaction possible, because there is no impact or impulse effect, only reaction. But here the diagram that is showing, here you have two sets, one is nozzle, another is blade, but here you see there is no blade, so only in the nozzle. So only in the nozzle, definitely the nozzle here, the nozzle is not moving, the nozzle is static. You see the stator, nozzle is stator. So these and these are not corresponding. That means this one is showing a pure reaction turbine, the top one, which is called Hero's turbine or Hero's engine. I am showing it. Is like this. Okay. So as if here you have a rotor. Let me enlarge it. They are basically same, so I can explain with any one of them. Say for example this one. So say it may be containing this lower vessel may be containing some water or maybe air also. So both are possible. Now if there is water, then if it is heated from bottom, say for example there it is showing that some wood is burning, so there will be heating and the water will be converted to steam. Now these are the columns, these two columns, through these two columns, the through these columns the fluid will the steam will rise. Through this column the steam will rise in this direction, and it will come in this chamber. Now within this chamber there it is connected to two jets, two nozzles. So the steam or air, hot air, now will come out through these nozzles, and therefore it will rotate in the opposite direction due to the reaction effect. So that is the thing. So through these pipes the steam or hot air is coming, and it is now ejected through these nozzles. Now as a result of reaction, this will rotate in the opposite direction. So this is a pure reaction turbine. These are called Hero's engine or Hero's aeoli pile. Okay. So this is one thing, but for power production in efficient way, this is not possible. So what we do basically is a impulse reaction turbine instead of a pure reaction turbine. Okay. Now this is impulse reaction impulse reaction. You see that pressure decreases, and in this case velocity increases. Because the nozzle cannot move, the velocity of the fluid increases. That means nozzle is not getting the share of velocity. But here these are also called moving nozzles. These blades are also sometimes called moving nozzles. So as if there is an expansion of steam through this nozzle, therefore these are sometimes called moving nozzles. So now as the fluid comes out and the nozzle can move, therefore the kinetic energy gained due to this uh, pressure drop will now be shared by the nozzle also. Therefore the absolute velocity of the fluid that is coming out will have less value, because it has imparted its kinetic energy to the nozzle. Okay, this is impulse reaction turbine. Okay. Now this is called basically the D-level turbine, the left one impulse turbine, and this is called the Parsons turbine.
স্যার আপনি যে আগে ফটোটা দেখালেন সেটা কি মানে ইম্পালস টারবাইন নাকি রিঅ্যাক্টিং টারবাইন?
কোনটা?
ইম্পালস রিঅ্যাক্টিং
Which one? Which one?
আগে আগে যে ফটোটা দেখালেন চলুন আগে দেখুন।
Is there any impulse? Here, is there any impulse? Impulse effect. What is the impulse effect? Impulse effect means nozzle after coming to the nozzle, it will strike the blade.
চেঞ্জ করতে পারবেন।
No. You try to understand that. Impulse means what? Here, impulse means after coming out through the nozzle, it is striking a blade. So, do you see any blade here? Do you see any blade here?
No, sir.
So, how can it be a impulse reaction turbine? This is pure reaction. Okay. Blade is not there. So there is no question of steam coming out from the nozzle and striking the blade. So there is no impulse effect. So we are not getting the motion due to impulse effect. We are getting the motion due to the reaction effect only. Isn't it? So this is pure reaction. Pure reaction turbine or pure reaction rotor. These are only for some demonstration or these are only some ideas, okay? But practically, you cannot use it. Or maybe for very small purpose, for low power production may be used. But in case of a high capacity power production, you cannot use it. So now there will be basically two types of turbine that we will study. One is in case of mechanical students, only the impulse turbine is there. Reaction turbine part is not included in the syllabus. But definitely you can listen. But for practice in the examination, I think only impulse turbine should be studied. Okay. Okay. So these are up to this is it clear? Is it clear? Effect of impulse and reaction. So what happens to the pressure and velocity? Is it clear now? Okay. So the first one is called the simple impulse turbine. This is called simple impulse turbine. Okay. And this turbine is called basically the D-level turbine. Okay. This is called D-level turbine. Okay. So in this D-level turbine, what is there? In this D-level turbine, see that it is one set of nozzle and one set of moving blade only. One set of nozzle and one set of moving blade. Now nozzle can be a single nozzle. Nozzle can be in numbers. Okay. In general, it is not that is distributed throughout the periphery. Only a few nozzles or a number of nozzles are there. It is not continuously distributed in general. Okay. So what is happening? You see that this is the nozzle. Now let us try to see. This is the nozzle. Okay. And here you see that there is a valve here. So this valve seat, this is the valve seat, and this valve can stop this. So this valve can close this path, and therefore the pressure that is coming from the boiler, the steam that is coming from the boiler can be stopped. So here the boiler steam is coming through this valve, but if the valve is closed, then the steam will be stopped. Okay, so that is a valve. So now this is the nozzle. The nozzle is actually like this in the meridional plane. It is like this. So these are basically two different views. This is a sectional view in the axial plane. I'm sorry, in the plane perpendicular to the axis. So this is the plane passing through the axis. So on this plane we are showing a set of nozzle and blade. Okay. Now the uh, this is the blade nozzle that is fixed, that is called the stator, and the blade is mounted on this turbine wheel. This is called the wheel. So this will rotate. So this is fixed to the shaft. This is the wheel and this is the blade. So blade is mounted on the wheel and the wheel is mounted on the shaft. So when the blade will rotate, blade will move, it will move the wheel and the wheel will rotate the shaft. This is the mechanism. And after that, it will come out of this chamber as exhaust and it will be condensed. So there are two types. One is called condensing turbine, another is called non-condensing turbine. Condensing means it will go to the condenser, and in case of non-condensing turbine, it will not go to the condenser, it will be ejected. Okay. So you see what is happening here. The velocity of the, this is the direction of velocity of the steam in the nozzle, and this is the direction, this is the direction of the velocity of the blade, and this is the direction of velocity of the steam in the axial direction. That means at the exit the steam will come out as an axial flow only. There will not be any tangential component. It is expected that there is no tangential component. So for maximum efficiency, the motion or the velocity at the exhaust or at the exit from the blade will be along the axial direction. So this is in the meridional plane, this diagram. This diagram is showing on the plane passing through the axis, the top one. This is the one which is on the meridional plane, and this is showing the pressure and velocity variation. As you have just seen the pressure variation. So this line, long chain dotted line, so it is showing a pressure drop. Then there is no further pressure drop. So you see that this passage is the one which is basically, let me show. This passage is for the blade and this passage is for the nozzle. So in the nozzle there is a pressure drop, but in the blade there is no pressure drop. So that is impulse turbine. So it is simple impulse turbine. So velocity, what is happening to velocity? Initially velocity increases because of the expansion, because of the expansion. And after that in the blade, due to the sharing of the momentum to the blade, the momentum and velocity of the steam drops. Now remember always that these are showing the pressure and velocity of the steam only. It is not that of the blade. Okay, that must be clearly understood. This is the velocity and pressure for the steam only. So at the exit, you see this is named as lost velocity because you see that there is some kinetic energy which is remaining to the steam, and that is carried over to the exit or exhaust. So that is a loss. So as there is a kinetic energy, we have not used that kinetic energy, that is called a loss. That is called lost velocity. We will see that is also called carryover loss. Okay, or leaving loss. Carryover loss. Or leaving loss. That means here you have some velocity with which it is going out. Therefore, it has some kinetic energy which is not used, and therefore it is a loss. So it is called carryover loss or leaving loss. Now you see that, as I told that the exiting steam should not have any tangential velocity, but there it will have some axial velocity, but that axial velocity must be as low as possible, because without any axial velocity you cannot extract the steam from the turbine. So there must be some velocity, but that velocity should be as low as possible for the maximum conversion of the energy that was there in the steam. If it is exiting with some velocity, definitely it is a loss in the loss of kinetic energy. Okay. So that is the diagram of simple impulse turbine. Now, what is the problem? You see, sorry, I'm sorry. There is one mistake. The lost velocity is this one. Okay, I'm sorry, because this is the velocity. Let me emphasize. You see, this is the velocity increased in the nozzle, and then velocity dropped in the bleeding stage, and it is exiting with this. So this is the actually this is the velocity with which it is exiting. Therefore, the loss corresponding to this is the carryover loss. And you will see that for a single stage impulse turbine or D-level turbine, that velocity is quite a high. Because of what? Because in one stage or in single stage only, all the kinetic energy that is gained by the steam due to the expansion, you have to convert to the blade. So there is a single stage, only one stage is there. So whatever kinetic energy has been gained by the steam, you have to transfer to the blade to minimize the loss. But in that case, the velocity of the turbine will be very high, maybe of the order of say, 30,000 RPM. Okay. So huh?
Yes.
Even in that case, there will be a substantial amount of loss as a carryover loss. The velocity will be high at the exit. Okay. So there is a problem with this D-level turbine. That means with the single stage, we cannot extract maximum possible energy. So what we do basically, we try to involve or try to employ stages in the turbine. So in the turbine, we will employ or install such stage like one set of nozzle, then blade, again a fixed blade and fixed blade and moving blade, fixed blade and moving blade, like that, to reduce the carryover loss. So that in that case, we don't have to convert the kinetic energy gained by the steam in a single stage. We will have the option of converting it in a number of stages, so that at the exit, the velocity will be less. The carryover loss will be less. The carryover loss is definitely is a kinetic energy loss, and therefore it is proportional to what? Proportional to V square or V square by 2, right? Because it is kinetic energy, so it will be of the order of, or means it is proportional to V square by 2 or V square. So there may be a substantial amount of loss due to that velocity, exit velocity. So what we do is we do a pressure compounded impulse turbine. Okay. So yes.
স্যার বলছি যে যদি মানে মানে যদি স্যার ওই মডেল থেকে যেটা বেরোচ্ছে স্যার যে লিকুইডটা, সেটার থেকে যদি
Not liquid. Not liquid. Here it is steam.
হ্যাঁ 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 স্যার স্টিম স্যার অবভিয়াসলি।
Hmm.
স্যার যে লিকুইডটা স্যার বেরোচ্ছে স্যার নজেল থেকে, সেই লিকুইডটা যদি স্যার ট্যানজেনশিয়াল ভেলোসিটি না থাকে স্যার, তাহলে স্যার ওটাকে ব্লেডটাকে স্যার রোটেট কি করে করছে?
মানে tangential velocity না থাকে মানে?
স্যার আপনি আরেকটু বলবেন?
হ্যাঁ, এটা তো এক্সিটে, এই যে এক্সিটে, this is at the exit from the blade, so it has already, the steam has already moved the blade and it is exiting the blade. Here there is no work to left to rotate the blade, it is exiting the blade. Here there is a tangential component, at the inlet there is a tangential component, but at the exit it should not have a tangential component.
Okay.
Okay. Before that, it must have a tangential component, otherwise it will not do the work, isn't it? After that, it has already passed and there is no work to do on the blade, so it is exiting simply as axial velocity. If that would have an axial velocity, that means what? If at the exit there is some axial velocity, that means all the axial component of kinetic energy we have not, all the axial component of velocity we have not converted or transferred to the blade. That means, so if there is some velocity which is, say for example like this, if it is leaving with some velocity like this, it means that part of the kinetic energy we have not used, it is leaving with that velocity. That means that is unused tangential component, or like this. Say if it is leaving with this, that means what? It will definitely leave. It will have some relation. So it will definitely has not been fully utilized. It has not been utilized fully. That kinetic energy, that corresponding velocity component, right? So it should exit as a as an axial velocity only, and that too will be very small quantity. That means that should be very small to have a loss, to have a small loss as a carryover loss. So you have to understand that this should be very small, right? Is it clear?
Yes, sir.
Okay, so this is called simple impulse turbine or D-level turbine. Okay, now we will go for the analysis of the D-level turbine. Before that, let me discuss the next one, that is called the pressure compounded impulse turbine. So pressure compounded means what? Basically, in the D-level turbine, the pressure reduction was done or conducted in a single nozzle. Okay. In case of D-level turbine, the pressure reduction is done in a single nozzle. In case of pressure compounded impulse turbine, the pressure reduction will be done in number of nozzles. In number of nozzles. Okay. So that is called compounding of pressure. That means basically the pressure reduction is done in number of stages. You see, I will explain it later. So you see that pressure reduction is done here. Again, pressure reduction is done here. Again, pressure reduction is done here. Okay. So this is called the pressure compounded impulse turbine, as the pressure reduction is not in a single stage. It is done in a number of stages. Okay, and as usual, in the blade passage, there is no change in pressure, because this is impulse turbine. So during the movement through the blade, there is no change in pressure as expected, because there is no expansion in the blade, so it is constant. But in the nozzle, or in the stator, there is a change in pressure, there is a change in pressure, there is a change in pressure, like this. So this is called pressure compounded impulse turbine, or this is also called.
এটা করে মানে আমাদের অসুবিধাটা কি হচ্ছে, মানে করছি কেন?
Okay. So what we are doing basically, you are not allowing in a single stage. The pressure reduction is done in a number of stages, and therefore you see that velocity increase here is very high, right? Due to that pressure fall. If the pressure fall is done or conducted in one stage, then the velocity will be also very high at the exit of the nozzle. Now, if I cannot transfer that kinetic energy to the blade, then it will be a loss. So what we are doing basically is, now we are basically reducing the pressure, but in a number of stages, or in steps. Okay, so the whole pressure is not reduced in a single stage or in single step. It is reduced in a number of stages, so that the velocity increase will also be, it will also be within limit, right? It will be also within limit. That means in one stage the velocity will not increase very high, so it will have a moderate kinetic energy at the exit of the nozzle, and it will now rotate the blade rotate the blade. Now what will happen in the next nozzle? There will be further pressure reduction and there will be further velocity increase. You see, I will explain it. So you see that this is the pressure compounded impulse turbine. হ্যাঁ, লস ভেলোসিটি তো থাকবেই। লস ভেলোসিটি না থাকলে, হ্যাঁ, অ্যাক্সিয়াল কম্পোনেন্ট হোক যাই হোক, আমরা যে কোনো যে কোনো কম্পোনেন্ট থাকলেই কাইনেটিক এনার্জি থাকবে। তার জন্য এখানে একটা বেসিক্যালি একটা একটা ইয়ে হবে, তার একটা লস হবে। কাইনেটিক এনার্জি তো স্কেলার, আমি আগের দিন বললাম না, কাইনেটিক এনার্জি হচ্ছে স্কেলার। তাহলে ওইখানে একটা লস হবে এবং সেই দ্যাট লস উইল বি বেসিক্যালি ডিউ টু দ্য এক্সিটিং ভেলোসিটি। So if there is no velocity at the exit, you cannot extract the steam. So for the operation, extract, you have to extract the steam, otherwise the steam will remain. How can you extract it? Isn't it? So to extract that, there will be some velocity at the exit. So you have to optimize, right? That means if there is no exiting velocity, then you cannot extract it. And if there is high exit velocity, then there will be a loss. So you have to minimize that loss. Yeah.
Yes, sir.
Okay. So that is why what we are doing is basically we are reducing the pressure in a number of stages, so that the velocity increase in the first stage will not be that high, so that after that it is not utilized and it is lost. So that is now that chance is now reduced. Okay, so that is called basically the pressure compounded impulse turbine. So what is happening, you see, let us first see what is the arrangement. So in this case, you see that these are called diaphragms. Okay, these are called diaphragm, means in which there is nozzle, that part is called diaphragm. So these are the hatched section, these are called the stator. These are the stator. You see that they are connected from the shaft. There will be gland, there will be basically ceiling here, and it is connected to the cylinder. This is called cylinder. These are called basically cylinder. In a turbine, there are different nomenclatures. So this is called cylinder. This is I'm sorry. This is called the cylinder. Although it does not look like a cylinder, but this is called a cylinder. Okay. So like if you have say two or more cylinders, we call multi-cylinder turbine, like that. So this is the cylinder basically, which is the casing of the turbine. Now in this case, always you will see that there will be two sets of such things. So one stage means basically combining these two. So one stage means basically one nozzle and one blade taking these two together, we call it a stage. So these two together, it is a stage. I'm sorry, it is only up to this. And again, on the next, this is another stage. Let me show you the different color, so it will be easy for you to follow. So this is one stage. This is another stage. This is another stage. So here you have three stages. So pressure is compounded here in three stages. First. Okay. Next, here again, after that, there is another set where you are basically doing compounding the pressure. So here one, here two.
পেপার কম্পাউন্ডিং বলতে গেলে মানে এটা তো ভেলোসিটি কম্পাউন্ড হচ্ছে।
No, velocity is not compounded. Velocity means what? Pressure. What is the meaning of velocity compounding? Velocity compounding means basically whatever increase in velocity happened, now we will reduce it or use it in number of stages. That is called velocity compounding. Whatever velocity is increased, we will see it. We will see velocity compounding, and then you will understand. Well, first, let us understand the pressure compounding. So what we are doing is basically, you see, what is the difference you see here and here? So in case of simple impulse turbine, the pressure reduction has taken place in one stage. Full pressure reduction, this is the condenser pressure, means exit pressure. So it is the pressure with which the steam will exit the turbine. This is called the condenser pressure or back pressure. So this is the boiler pressure. This is the boiler pressure. This one. This is called the boiler pressure. And this is the condenser pressure. So the pressure reduction from the boiler pressure to the condenser pressure, this is happening in one stage only. This is called simple impulse turbine. Now, if I break this in number of stages, it is now happening in number of stages. So pressure reduction is happening in what? These are impulse turbines. So pressure reduction will happen in the nozzle only. So there are number of nozzles. Number of nozzles here. You see this one, this one, this one. So this is one stage, this is one stage, this is one stage. Again, you have one stage, another stage. So basically, what is happening is that the pressure reduction is now taking place in number of stages, but velocity is changing due to the expansion and due to the conversion of kinetic energy from the steam to the blade. That is the impulse principle. That is not velocity compounding. Velocity is changing due to the impulse effect and the conversion of kinetic energy from the fluid to the blade. So that velocity change is not that is not compounding. Okay. Only follow the pressure. Okay. So okay. So here the pressure is reduced in a number of stages. So this turbine is called Reto turbine or Reto turbine. So earlier one we were calling that as D-level turbine. Here it is called Reto turbine. So what is that? Reto turbine. So means it is after the name of a Reto. So a Reto turbine. That means Reto turbine means basically pressure compounded impulse turbine. Next, we will see the another one which is called the velocity compounded impulse turbine. Now, in this case, what is the difference you see? There is a nozzle here as usual. In all impulse turbine, there will be a nozzle which is connected to the boiler and the steam chest. Now there is a wheel. This is called a wheel. You see the difference. This is a wheel which is connected fully to the shaft. Now, this wheel has basically 3 rows of blades. Here it is 3. 1, try to understand. This is a single wheel. Let the diagram be clarified a bit. Okay, I think you can see. So this is a single wheel. Full wheel is connected to the shaft. Okay, now it is having one blade here. Then there is another set of guide vanes or guide blades, or basically these are stators. Stators are connected to the cylinder, you see. So this one, the second one, it is connected to the cylinder. Let me color it so that you can follow. Say red. This red 1, 2, and 3, third. This is connected to the wheel. Here, it is connected here, here, and here. And this one, this is second, because the nozzle is the first, then it is the first. So this nozzle is the first, and then it is the first. The first stage, this is first stage. Then second stage is this one, comprising of this fixed blade and this moving blade. Okay. Next, what we have, now you see that there is no, instead of nozzle, there is blade only. Do you follow the difference? In case of pressure compounding and velocity compounding, in case of velocity compounding, this is velocity compounding or velocity compounded. Here you have basically, let me show you the different color so that you will be able to follow. It's a green. And this is the third stage, blade. And the third stage, fixed blade. The green is fixed blade. And the nozzle is definitely fixed. Nozzle is not moving. So this green, one tick, they are comprising the first stage. The green double tick and the red double tick, they are comprising the second stage. And the green three tick and the red three tick, they are comprising the third stage. Okay. Now you see the difference. In case of velocity compounding, this is a fixed blade, nozzle, not a nozzle. Because in a nozzle, there is pressure reduction and velocity increase. But these are fixed blade. There is no pressure reduction. There is only diversion. That means deflection. Okay, do you follow? You see, you see the difference. That here, in case of pressure compounding, instead of that, you have basically all are different wheels. Here you have basically diaphragm. So this first nozzle is this one, and then red, so it is 2, then it is 3. And accordingly, the red one I mark, this is 1, this is 2, and this is 3. Now you see that the wheel 1, wheel 2, and wheel 3, they are separately connected to the wheel, to the shaft. They are not a common wheel, right? And they are separated by a diaphragm, right? These diaphragms separate two stages, right? This diaphragm basically separates two stages. So the steam cannot go. The steam can go through this nozzle only, and it will strike the blade and it will move it. Then again, there will be expansion. Again, there will be expansion in the nozzle. Again, there will be, that means expansion means pressure reduction and velocity increase. Again, there will be strike on the blade and momentum transfer. Again, it will go through the nozzle. Again, there will be pressure reduction and velocity increase. And again, there will be impact, or that means on the blade, and there will be a momentum transfer to the blade. So that is happening here. All these are basically nozzle. So you see that this is a nozzle. That green one is a nozzle. So this is a nozzle instead of blade. This is 2, this is 3, the third stage. And these are blades. These are impulse turbine blades are like this. We will study when we will see the geometry, we will study the impulse turbine blades having this characteristic. It is symmetrical almost. Reaction turbine blades will be different. We will see it. Just for your first have first time experience, you see it, you see that this is the impulse turbine blade. It is like symmetrical, but reaction turbine blades are not symmetrical, they are asymmetrical. So that will be a visible difference between the impulse turbine blade and the reaction turbine blade. Okay, now you see that what is happening in the pressure compounded turbine. These are basically nozzles.
প্রেসার কম্পোনেন্ট ভেলোসিটি কম্পোনেন্ট তার মানে কোনো নজল একটাই থাকে
একটাই।
স্যার
So
ফিক্সড প্লেট
বাকি in the fixed plate there will not be any pressure reduction because it is velocity compounded. You are converting, or you are basically reducing the velocity in number of stages. So basically follow the first one. This is the most critical or pivotal diagram, that is the simple impulse turbine. You see, in the simple impulse turbine, there is in one stage only there is a pressure reduction and velocity increase, and after that in the blade there is velocity decrease due to the momentum transfer to the blade, moving blade, and after that it is a loss. Now this will be now used in number of stages for velocity compounding, and in case of pressure compounding this will be conducted in a number of stages or steps. That is the thing. So how that is to be done is, for pressure reduction we know that is done by a nozzle. So if it is pressure compounded, then there will be a number of nozzles, means all the stages there will be nozzles. Okay. And in case of velocity compounding, basically there will be blades instead of nozzles, because there is no requirement of pressure reduction. There is only requirement of momentum transfer. So you see that this is the arrangement of fixed blade and moving blade. So this is nozzle. Exactly. You see that is the pressure reduction only once, because there is only one nozzle. So there is only one time pressure reduction, and that is, you see that exit of this nozzle, that is the pressure is same as the condenser pressure here. That is the condenser pressure. After that there is no pressure change. Do you follow? There is no pressure change, constant. So this is velocity compounded, and pressure is reduced in one stage only. After that there is no pressure change. Okay, but you see that what is happening to the velocity? Velocity increases in the first nozzle. Velocity, that means in the nozzle the velocity increases as expected, because the pressure has reduced, therefore velocity will increase. Now from this what happens, you follow. Now let me show you the different color so that you can easily follow. See that velocity increased due to what? Pressure reduction. Due to expansion, velocity increase. Now what is happening here? What is that? This is a moving blade. First stage, moving blade. So during the moving blade interaction, as the kinetic energy or momentum of the steam is transferred to the blade, the momentum and kinetic energy of the steam will reduce definitely. So there is a reduction. Okay. Now in the guide blades, there should not be any change of momentum and kinetic energy. It should almost go means the same value, but it is considered that during that movement there is frictional loss. So due to friction there is a little reduction in velocity, but it is not as much as that was in the moving blade. So in the fixed blade, what is happening? You see, in the nozzle, the steam is coming here and it is striking. So due to the impulse principle, it will rotate. Now as it is moving in this direction, it will release the steam in this direction. So it is going in this direction and it will release the steam in this direction. It will now be striking the fixed blade, and now the fixed blade will now divert the fixed blade. This is fixed blade. So this one, fixed blade. So green. This is fixed blade. Now this will divert the steam in this direction. Again, it will act like a diversion, and now it will produce the impulse effect here. It will produce the impulse effect here, and it will rotate, and again the steam will come out from the next stage of moving blade in this direction. It will Now strike here. Now it will come out from this as diverted one. Now it is said that during this movement or during this diversion on this blade due to friction, there will be some loss. So that is shown here. You see that this is the little loss that is in the guide blades or the fixed blades that is happening. So velocity reduction is happening due to friction here. That is not due to the mechanical conversion. That is due to friction. Okay, do you follow this? This is in the guide blades or the fixed blades. This is in the moving blade. In the moving blade, there will be a substantial reduction in velocity due to transfer of momentum to the blade. So the momentum and kinetic energy of the steam will be reduced. Again, that is happening in the second stage. So these two is the first. You see, say this is 1, this is 2, this is 3. And let me show the moving blades. So this is 1, this is 2, and this is 3. So what is happening in the next moving blade? There is a reduction of velocity due to what? Due to the momentum transfer from the fluid to the blade. So the blade is gaining kinetic energy and the steam is losing the kinetic energy. There is an exchange of kinetic energy and momentum. So the blade continues to move, and that means the blade continues to receive the kinetic energy and momentum, and the fluid continues to lose its kinetic energy and momentum. Therefore, it goes on. So that way, basically, you see the velocity increase was done in one stage in the nozzle. After that, the velocity reduction was done in a number of stages. So that is why it is called velocity compounded impulse turbine. Do you see it clearly?
Yes, sir.
Okay, and see, the effect is that at the exit, the lost velocity is much less compared to the earlier one.
একদম মুভিং বিলটা জেনারেটর লাগানো থাকে।
Huh? Even here also, you see that there is a lost velocity which is large in case of pressure compounded, because at the exit, what is happening? Due to the expansion, there will be high kinetic energy, isn't it? So due to the expansion, the kinetic energy of the steam will increase, and after the impulse principle, that will be exiting with a high velocity. So full kinetic energy conversion will not be possible, and it will be exiting as a high velocity. So even in case of pressure compounded turbine, there will be loss. That means carryover loss will be more. But in case of velocity compounded turbine, you see that what is happening? The pressure reduction was done in a one stage. So there is no question of further employing of or installing of nozzle. Only one nozzle was there. After that, there was only diversions of the blade, diversion of the steam by guide blades. So moving the fixed blade, moving the moving blades or rotating the moving blades by use of diverted steam using the guide blades or the fixed blades. So these are basically fixed blades. This is called a 3-row wheel. 3-row means 1 row, second row, third row. This is called a 3-row wheel. Similar to that, there are 2-row wheels also. This is called a 3-row wheel. Why? Because this is a wheel, single wheel, and it has 3 row of blades. 3 row of blades. That is why this kind of arrangement is called a 3-row wheel. This arrangement is called a 3-row wheel. Similar to that, it can be a 2-row wheel also. Okay, 2-row wheel also. So two row wheel means basically there will be two sets of blades, moving blades in the wheel connected to the wheel. So there will be one nozzle. After that, there will be one moving blade, and in between there will be a fixed blade or guide blades, and there will be a moving blade. So it will be up to this. It will be up to this. So in a two row wheel. So it is experimentally seen that a two row wheel has more efficiency compared to three row wheel. So what is done is we give another we get another variation of impulse turbine, that is called pressure velocity compounded impulse turbine. That means in a turbine, the pressure and velocity both are compounded. We will show it. So this is a wheel. This wheel is connected to the shaft. There is a key. It is key to the shaft. That means as the blade will rotate, blade will move, that will move the wheel, and that will move the shaft. The shaft will rotate. Okay.
সেখানে তো আমরা স্টেজে মানে স্টেজে যে ভেলোসিটি কমছে বললে আমরা হচ্ছে যে আরপিএমটা কমে যাচ্ছে জেনারেটরের।
Yes, RPM will be less within motor. That means what is happening? RPM, say if in a single stage turbine the steam is coming out with say 4,000 feet per second, and the steam turbine is rotating at say 30,000 RPM. It is not necessary, isn't it? No such device is there which is needed to be rotated by say means it is very less. That means you need to rotate the machine at 30,000 RPM. So it is unnecessary. But the steam speed is such high that the velocity will be either it will be converted to the rotation, or it will exit with a loss. So what we do is basically we break it in a number of stages so that it will rotate the blade and the torque will be generated, but it will be in a number of stages, and also the speed will be reduced. Efficiency part of course means you will basically utilize the energy efficiently. The efficient means loss will be less. Okay. So you see that there is another kind of okay, is it clear? So this is called velocity compounded turbine, or this is also called basically Cartesian turbine. This is called Cartesian turbine, after the name of Mr. C.G. Curtis. An American engineer, C.G. Curtis. So it's called Curtis turbine. That means a velocity compounded impulse turbine. Okay. Next, we will have a pressure velocity compounded impulse turbine. So here, there will be basically compounding of both. Okay. So this is called basically pressure velocity compounded impulse turbine. Okay. So why it is done basically, as I told you, that two row wheels are more efficient than the three row wheels. So here you see that here basically in the first velocity compounded stage, we are using a two row wheel, and again there is a further pressure reduction by using a nozzle here. So this is the first nozzle. That means for the first velocity or the first velocity compounding stage, so there is a nozzle here. Now here the velocity is compound, the pressure is reduced. So here the pressure is reduced. Again, the pressure is reduced here. So pressure reduction is done. So it is pressure compounding. That means two nozzles are used. So it is pressure compounding, as well as here we are using wheels. So it is a two-row wheel. You can see two-row wheel means one, two. Again, here you have one and two. So it is both pressure compounding. So in one stage, you have first pressure reduction, and then there is velocity reduction in two stages. Again, there is a pressure reduction and velocity reduction in two stages. So it is both pressure velocity compounded impulse turbine. So you see that there is a nozzle here, and then it is the moving blade. This is the moving blade. Then there is a set of uh, guide blades, the guide blade, and again moving blade. So moving these two moving blades, you see, uh, this one and these two together, it is comprised the two-row wheel. So this is the wheel has two row of blades. So it is a two-row wheel. Again, it has the in the next pressure compounded stage, uh, in the next velocity compounded stage, there is basically a two-row wheel. So one and two. These are the moving blades. And this is the uh, fixed blade. Fixed blade, here fixed blade stage 2. Here it is stage 1. Here it is stage 1. Now you follow the pressure and velocity variation. না, these are blades. এইটা হচ্ছে নজল একমাত্র, this is not. না, red mark, I have marked red for this also. This is the nozzle. This is the nozzle only. Okay, let me show with the color. This one. You see that this is nozzle. The green. Okay. Again, this is the nozzle.
Yes, sir.
This is the nozzle. Okay. This is the nozzle. This is the nozzle. So in the nozzle, nozzle is like, you see, the nozzle will have a tangential direction because it has to create a velocity in the tangential direction. So nozzle will be oriented along the tangential direction. But in case of guide blades, they are basically for impulse turbine. The guide blades are symmetrical. Guide blades are also symmetrical. So that is the difference. So this is guide blade. This red color, this is the guide blade, not, you see, let me with a different color show. These are guide blades. দেখা যাচ্ছে কালারটা, এই যে ব্লু কালার, these are guide blades. These are not nozzles. These are guide blades. A nozzle, যতগুলো nozzle থাকবে, যদি if there are number of nozzles, if there are number of nozzles, then there will be pressure compounding or pressure compounded. Okay. If there are guide blades, then this is basically velocity compounded. Okay. So you see the difference here. That is here. Let me show with colors. Show with marking. So this is what marking we were using. Uh, green for the nozzle and the fixed one, and the red for the moving ones. Okay, green for first one. So you see that green. This is the nozzle, first nozzle. Then second stage. Then again in the nozzle, say this one, this is the nozzle. I'm using different symbol. So it was a tick and there is only prime. Uh, so it is double. And in case of the moving ones, it is first stage, then second stage. Again in the next uh, stage after pressure compounding. So there is one and there is two. So what is happening? You see, the pressure is reduced. This is the pressure reduction. Pressure is reduced once and the velocity increased. After the velocity increase, that velocity is utilized in two stages. And in the guide plates, there is frictional loss. So after the velocity reduction, it goes there. Again, there is a pressure reduction. Again, therefore, there will be some velocity increase. And that velocity, that means that kinetic energy now will be splitted in two stages, 1 and 2. This is 1 and this is 2. So that velocity is splitted. The kinetic energy is utilized in two stages. So this is called velocity compounding and this is called, this is one, this is called pressure compounding. This is another two pressure compounding, and in each of them there are two row wheels, so two stages of velocity compounding. Okay. Okay, is it clear?
Yes, sir.
So any question? Today we will stop here after the discussion, and tomorrow or the day after we will solve the or derive the quantities, different quantities like efficiency, etc.
The left hand side put a first stage, second hand side a second stage.
This is the first stage of pressure compounding. This is the first stage of pressure compounding. A pressure compounding is happening in two stages. So this is the first stage of pressure compounding, and this is the second stage of pressure compounding. Now, in each stage of pressure compounding, there is individually velocity compounding. So again, there in each of these pressure compounded stage, there are two velocity compounded stages. One and again for this. Okay.
Yes, sir.
So is it clear therefore? So you have to understand these things. That means the diagram. That means you should be able to read the diagram. That means what are the how the pressure and velocity are varying in the stages. What are the names? So say let me just spend a few minutes on the names. So in case of simple impulse turbine, what are the names you see? This is exhaust. This is boiler steam. That is quite clear. This is turbine blade. Blade will rotate. This is turbine wheel. The blade is mounted on the wheel, and this is sub. These are common nomenclature. This is simple turbine. Then you have basically the pressure compounded turbine. Here you have basically diaphragms. On the diaphragms, there are nozzles. So in each stage, there is a nozzle. So they are basically this one diaphragm is separating one stage. That means this diaphragm and this diaphragm, they are basically holding the wheel. Okay. So the steam is means basically they are completely separated. So these are called diaphragms. Within the diaphragm, there is a hole that is acting as the nozzle. And after that, there is basically wheel, and on the wheel, there is the blade. Okay. And as usual, there will be turbine shaft and the casing. This is called the cylinder. Okay. Next, we have basically velocity compounded impulse turbine, where you have basically a 3-row wheel or a 2-row wheel. That means you have a single wheel on which three row of blades are there, so it is called a three row wheel. If there are two row of moving blades, it will be called a two row wheel. This is the nozzle, and the in between the blades, moving blades, there will be basically guide blades. These are guide blades, or these are also called fixed blades. Okay. Here you see that it is called fixed nozzle. These are also called fixed nozzle. In case of reaction turbine, we will see that there will be basically moving nozzles. Means there will be expansion and we will see moving nozzles. So that we will see. Now there will be different arrangements for governing. Governing means for reduction of speed, that means control of speed. So to control the speed, you need to control the flow rate of steam. So there are different arrangements. So nozzle control, governing, etc. So there will be basically controlling the amount of steam, because the speed depends on the amount of flow. So mass flow rate, if we can control, then that will basically control the speed of the turbine. So the different arrangements are there to control the flow rate of steam. So there are, say for example, number of nozzles. So through these there are two nozzles. Through these there are four nozzles, like that. So to control the speed, you need to control the flow rate. Sometimes you may need to stop it fully, and you will just open this one, like that. So you see that in this diagram, this is fully closed and this is only open, so the steam is coming, and so therefore the torque will be definitely, the produced torque will be definitely less. So as you can see that if there are six nozzles and there are two nozzles, definitely through two nozzles, the using two nozzles, you will definitely get a less torque compared to six nozzles. Okay, so I think we can stop today.
So these are all isentropic flow.
Yes, yes. Theoretically, it is isentropic. Theoretically, it is isentropic. Practically, it is adiabatic. Okay. There will be some friction. Practically, there will be some friction. So frictional losses will be there, but more or less that will be considered adiabatic. So isentropic means basically reversible adiabatic, but it is not reversible due to friction, but it will almost remain adiabatic.
Okay, sir.
Okay.
Yes, sir.
So I think we can leave.
Yes, sir. Good night, sir.
Good
Thank
night.
you, sir. Good night, sir.
Good night. Hmm.
ডাউনলোড করবো
কোনটা?
পাইথন পাইথন
বুঝতে পারছি না, আরেকবার বলো।
পাইথনটা কিসে ডাউনলোড করবো মানে কিভাবে ডাউনলোড করবো পাইথনটা
ও পাইথন, আচ্ছা আচ্ছা। পাইথন
তাহলে
তোমার দেখো
আমার মিনি মিনি পেজে